Good morning, student. Today I am going to explain gate logic. So this is also one of the type of building blocks circuits. So we already learned switch logic, and this is another, that is gate logic. So gate logic is also called as restoring logic. Okay, so this is a logic circuitry designed so that even an imperfect input pulse, a standard output occurs at the exit of each successive logic gates. Okay, so what is the meaning of imperfect input? Suppose, so usually we will give a input 5 volts, correct? No, so what we will expect exactly 5 volts, but sometimes imperfect input means 4.2 volts or 4.3 volts will give an input. Okay, but then also we will get the exact 5 volts. The remaining 0.3 volts or 0.2 volts, these are restored in the output. Okay, that's why this is also called as restoring logic. Okay, and then the gate logic is based on the general arrangement typed by the inverter circuit. Okay, so these are the general arrangement by the inverter circuit we are considering in gate logic. So inverter means what? If you give a 0, you will get output 1. So if you give 1, you will get the output as 0. Okay, so that is an inverter. Okay, here we are using examples: inverter, NAND operation, and NOR operation, AND operation, and OR operation. Different examples we are considering in the gate logic. And also we are using different technology like nMOS and CMOS and also Bicmos. Okay, so now look into the first one, that is nMOS inverter. Okay, so in nMOS inverter, this is the circuit diagram. Okay, so this is the circuit symbol, and this is the logic symbol of inverter, so with the one bubble, and then this is the stick diagram. Okay, so first I will explain the circuit diagram. See here in the circuit diagram. Okay, so this is the inverter circuit. Okay, please remember, so this is the inverter circuit. I am using nMOS technology here. Okay, so here I am considering depletion mode of nMOS transistor I am considering. See here, the thick line is represent the depletion mode of transistor, and here this is the enhancement mode of transistor. So enhancement mode of nMOS transistor. Okay, so here okay, the circuit is now understood. No, I will explain how it will be work and all. And this is the inverter logic. So here we can also use 4:1 and also 8:1. Okay, so this is the stick diagram. So how we will draw the stick diagram? See here, so this is the VDD. The VDD and the ground I am mentioning here is a blue line. Okay, that is a metal. Okay, so this is the metal, and also this is the so this is the nMOS transistor. No, nMOS transistor how we will represent in green color. So write a straight line in the nMOS transistor. Okay, in that we have to draw the this one. What is that? Polysilicon. Okay, so make it as a polysilicon red color, and then here you have to draw the yellow box here. Okay, so this yellow box is indicate the depletion, so that is implant. Okay, so this is the yellow box, you have to write it here, and this is the contacts. Okay, so this is the contacts. This is the gate, no? So this is gate. This gate is connected. So this is a gate, and this is the drain, and this is the source. Okay, this gate is connected to output. Okay, this gate is, so this gate is connected to output. That's why V out. Here I'm connecting V out. Okay, and this is the 4:1 and 1:1 I'm using. So 4:1 is nothing but, so length into width. Okay, this is the ratio, length into width, that is 4:1 and 1:1 I'm considering. Okay, why I'm considering 4:1, not I'm not considering here 1:1, because of the proper output we can consider 4:1, either you can consider 8:1. Okay, so next I will explain the both the 4:1 and also 8:1. So what is the difference in 4:1 and 8:1 length and width if I'm taken. Okay, so now I am explain the stick diagram. So here the output, so this output. Okay, here I'm considering output, and again one more nMOS transistor I have to draw here. So this is the nMOS transistor. When the n diffusion is cut the polysilicon, here the transistor is formed. Okay, so this is the one more transistor. So two transistor is formed, and this is the output and this is the input. So here V in is there, so this is the input. Okay, understood the stick diagram. Okay, now come to the circuit. In the circuit, for example, if I am giving V in as 0 volts, okay, so what I'm expected the output here, if I give a 0, the output should be 5 volts, or it may be 1 volts. Okay, 0 means 5 volts. 0, if you give 0, the complement output should be 5 volts. 5 volts are equivalent 1 volts. Okay, that means, see, if I give a 0 volts here, the nMOS switch will be opened. Okay, here the nMOS switch will be opened. Okay, if it is open means it will not connected here, and here the closed path will be occurs. So here this path will be closed. Okay, so this path will be closed, and here the 5 VDD is 5 volts. No, this path is closed means the output will be appear like this. Okay, so I will get 5 volts. Okay, so if you give 0 volts, the nMOS should be, the nMOS transistor should be opened, and this will be opened and this will be closed. The closed path is connected to the VDD, and this VDD is connected to 5 volts. Okay, so if you give 0 also, I will get 5 volts. So 5 volts means it's equivalent to 1 volts. Okay, suppose if you give 1, V in as 1, what will be your output? The output should be 0 volts. Okay, if you give 1 volts, the output should be 0. So here the inverter you are using, that means complemented output you will get, no? So if you give 1 volts, the nMOS is acts like a closed switch. Okay, so here it will be a closed switch. Okay, and this closed switch is connected to the ground. Okay, so ground means 0 volts. Okay, you will get 0 volts. Okay, you will get 0 volts. Okay, if you give 1, this will be closed. nMOS is acts as a closed switch, and then you will get 0 volts. Okay, so this is the working of the nMOS inverter circuit. Okay, then, and also I have to explain in that, see here in the nMOS, here I am considering, okay, 8:1 nMOS inverter. So 8:1 nMOS inverter circuit, and also 4:1 inverter. Okay, using nMOS circuit. Okay, I already told we can length and width we can change in only in nMOS, not in CMOS, only in nMOS. Okay, we are designing nMOS, CMOS and Bicmos technology. 3 technology we are using here in the inverter. So in the nMOS I am considering now 8:1. Okay, here, so if it is nMOS means this is the polysilicon. Okay, so this is the polysilicon, and this is the, what is this? So this is the polysilicon, and this is the N diffusion and polysilicon I am using here, and this is also N diffusion and polysilicon I am using, and this is my pull up region and this is my pull down region. That means this is the top one is there, no, so this is the pull up region and this is the pull down region. Okay, so here I am considering, so length is 16 lambda and the length is 16 lambda and the width is 2 lambda. Okay, so this is the length and this is the width. Okay, so and the gap is there, no, so after that this is the pull down. So pull down is 1 is to 1, 1 is to 1 means 2 lambda by 2 lambda they are taken. Okay, see here, so we have to find out the power dissipation. Okay, so power dissipation, before that we have to find out ZPU. So this is the pull up impedance. ZPU is equal to length of the pull up is divided by width of the pull up, so that is equal to 8 ohms. So what is the this one pull up you will get, so pull up you got actually, see here, so ZPU is the impedance, so LPU is divided by WPU. So LPU is so LPU is 16, so how much length you have? 16 lambda, so take it as in 16, and the width is 2 lambda. Okay, the overall width it is, okay, that is 2 lambda they are cutting only, so here you can consider only 2 lambda, so divided by 2 lambda, that is equal to 8. Okay, that 8 they mentioned here. Okay, then again we want the resistance of the this one, overall resistance of the pull up resistance. RPU is equal to ZPU into RS. So RS is the sheet resistance. So for the sheet resistance here I am considering 10K. Okay, the sheet resistance I am considering 10K. It is a standard value 10K. Okay, so 10K is a standard value. So ZPU I got 8. So 8 into 10 is 80. Okay, so 80 I got. So similarly you have to do for the pull down also. So pull down you have 2 lambda into 2 lambda. Okay, so find out here, so the pull down, so ZPD is equal to pull down, length of pull down is divided by width of pull down, so that is 2 lambda by 2 lambda, that is equal to 1. Okay, so what is the resistance we have to calculate? No, so resistance of the pull down is equal to ZPD into RS. So ZPD is 1 into RS is 10K. So this is the standard sheet resistance. So I got 10K. Okay, so the total is I got 10K. So 10K pull down I got 10K. The pull up resistance I got 80K. Okay, so finally I have to find out the power dissipation. Okay, so power dissipation PD is equal to voltage is divided by the total resistance. So V square is divided by RPU plus RPD. So RPU I got how much? 80 plus 10K, so totally 90K. So here I am considering voltage as 5 volts. So 5 volts is a standard voltage, 5 volts. That's why I'm considering 5. So 5 square means 25. So 25 is divided by 90K. So 25 is divided by 90K, approximately you will get 0.000277 something 8 you will get. So then finally you can write it 0.28 milliwatts. Okay, so this is the value for the power dissipation. Okay, 0.28. So you got it here, no, 0.28 milliwatts. Okay, so here the input capacitance we have chosen 1 standard of CG. Okay, capacitance. Okay, so this is the 8:1 lambda. So the alternate is there. So for the alternate is 4:1. So what is the, so here the area is 8:1 is consuming more area, so here it is consuming less area. Okay, so but what is the problem? The problem is the power dissipation problem. So look at here, so this is also similarly we have to do it. ZPU is equal to LPU is divided by length divided by width. Okay, so the length is 8 lambda, so 8 lambda is divided by 4 lambda, so 8 lambda divided by 8 lambda, sorry, 8 lambda divided by 2 lambda, so 8 by 2 is, we will get 4. Okay, so then RPU is equal to ZPU into RS, so 4 into how much it is, so 4 into 10, so that is 10k, so standard of sheet resistance is 10, so 40. Okay, 4 into 10, 40. Similarly, you have to do it for the Z, this one you have to do it for the Z. What is that? ZPD is equal to LPD is divided by width of PD. So width, length how much? So the length is 2 by 4. 2 by 4 means we will get 0.5. So 0.5 into 10. So 0.5 into 10 means you will get 5k. So 5k you will get. Okay. So 0.5, 2 divided by this one means you will get 5k. So this 5k you will get it here. Okay. So the now the power dissipation P is equal to V square divided by this one. So this one how much you got? 40. 40 plus 5 is 45. So 25 is divided by 45. Approximately you will get some 0.5 milliwatts. Okay. So see the power dissipation here 0.56 for the 4:1, but here the power dissipation is 0.28. Okay, so because of the power dissipation we are choosing different values. Okay, so the next is CMOS inverter. Okay, so now I understood the nMOS inverter, right? So now we will move on to the CMOS inverter. So CMOS means we are considering here complementary. So the complementary metal oxide semiconductor. Okay. So here this is the pull up region and this is the pull down region. So pull up transistor and pull down transistor. Okay, so PMOS and nMOS and together with gate is gate and gate both are shorted, and here I am giving input and this is my output. Okay, this is the as usual same symbol inverter, and this is the stick diagram. Okay, see here, so VDD and VDD blue line, and this is the PMOS, that's why I'm considering as an yellow, and this is the nMOS, that's why I'm considering as an green line, and the blue is the output. Okay, so this one blue is the output. So the output is indicated blue line, and here the polysilicon using, here it forms the transistor, and here also one more transistor, here the PMOS transistor and here the nMOS transistor. Here I'm giving a input, and this is the demarcation line. So the demarcation line is different, differentiate the pull up region and pull down region. Here I am considering the length into width is same. Okay, so here not here in CMOS we can't able to take a different, so here we are considering only 1:1, 1:1 only. So length into width. Okay, that is 1:1 and 1:1. So here how it will be work, suppose here if I give a 0 volts. Okay, so what will be the output you are expecting here? If you give 0 volts, I am expecting here 5 volts. Okay, 5 volts means that is a 1 volt. Okay, so if I give a 0 volts, so my nMOS is opened, because if this is nMOS is strong in ones, weak in zeros. Okay, but the PMOS is strong in zeros, weak in ones. That's why if I give a 0 volts, this will be opened. Okay, the nMOS will be opened and the PMOS will be acts as a closed switch, and the VDD 5 volts will be closed, and the output I am getting here 5 volts. Okay, so next, suppose if I am giving 1 volts. Okay, so if I give a 1 volts, here this will be acts like a closed switch. Okay, and this is the open switch, and if it is a closed means it will be, the path is like from ground to here. Okay, the ground to here, the ground is 0 volts. If I give a 1 volts, I will get a 0 volts. Okay, so this is the CMOS inverter works. Okay, so the last one is the Bicmos. Okay, so Bicmos is nothing but, so Bicmos is complementary metal oxide semiconductor. Okay, so here the circuit is same as a CMOS only. Here we are just connected the BJT. Okay, BJT I am considering here. So these are connected to the BJT. See here the connections are like this. VN is shorted and this one is connected to the gate of the this one. So this is the emitter, base and collector. Emitter, base and collector. Emitter, base and collector. Okay, so why these are connected to the BJT? Because the BJT transistors are mainly used in terms of enhancing the output. Okay, so we have to enhance the output. We are just considering the BJT. Okay, so this is the stick diagram. So this is the VDD and this is the VDD. So as usually whatever it is the circuit, right, same you can write. So this is the VDD means blue color, this is also blue color, and this is the PMOS I'm using, PMOS. So this is the PMOS. This is the nMOS, green color, and this is the polysilicon. Here the transistors is formed. This transistor PMOS and nMOS is formed, and this is the transistor, that is a BJT 1 and BJT 2. Here I am considering. So this is the explanation is not needed. For the more explanation is not needed, because see, the circuit is very complexity, no. So that if the circuit is complexity, and also the cost will be more. So that's why we are not much used in Bicmos. Okay, we are just concentrating only on the CMOS and nMOS circuit. Okay, understood? If you have any doubt, you can call me. Thank you.